Hey folks, Titmus here. In this lesson, we're going to learn how to use scientific notation and SI prefixes to write and discuss very large and very small numbers. Let's do it. To start, let's understand why this is even a problem. The distance from Sherwood High School to the movie theater is about 1 mile. Now multiply that by about 8,000 and you have the diameter of the Earth. Multiply that by about 100, you get the diameter of the Sun. And then multiply that by 100 again, and you have the distance between the Earth and the Sun. But this is only half the problem. You see, you could fit nearly 1,000 people head to toe between the school and the movie theater. And you're about 10,000 skin cells tall. So already we have a scale factor of 800,000 million. And we haven't even started talking about atoms or galaxies. Is your head starting to hurt from the numbers? Mine is. So let's take a closer look at the sizes of atoms and galaxies. An atom can be as small as 1/10,000,000th of a meter across, and our Milky Way galaxy is over 1 billion trillion meters across, and we've got a small galaxy. That's a ton of zeros to write, and comes with a few problems. First, it takes a long time to write. Second, it takes up a lot of space on the paper. And third, counting is hard. And you'll see that because I make a mistake here in a second. So, here's what we can do to deal with long numbers, big numbers. Instead of writing out all those zeros, we just count how many times we had to multiply by 10, and we write that down. So this big number, we take 1 and multiply it by 10, and we do that 21 times over. Each time we multiply by 10, it puts a 0 on the end of the number. So we can just count the zeros, which is harder than it looks. The scientific notation here effectively tells us how many digits long our number is, or how many zeros there are. Now for small numbers. Instead of multiplying by 10, we have to divide by 10. And in this case, we divide by 10 times. We can rewrite this as 1 times 10 to the negative 10, where the negative in front of the exponent tells us that we're dividing. So, let's take a look at a few examples going back and forth between standard notation and scientific notation. Here's the mass of the Earth, 5,972 billion trillion kilograms. And what we can do with any number that doesn't already have a decimal point is just write in the decimal point at the end of the number. Then, we count how many times we would need to move the decimal point to the left until it sits just after the first digit, just after the 5. So we count that out. I like to draw it while I count so I don't skip anything. And we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 moves. So this giant number becomes 5.972 times 10 to the 24th kilograms, which is way easier to write. Okay, let's talk for a second about the parts of this number. The 5.972, we call that the magnitude. That's the number part. And then the 24, we call that the exponent. Okay, so those are important terms. Now, sometimes we need to take numbers from scientific notation and put them back into standard notation, which is just a normal number. Let's take a look at one of those. So here's the distance from the Earth to the Sun, 9.3745 times 10 to the 7th miles. Now what I'm going to do is write down the first part of the scientific notation number, the magnitude, 9.3745. Then I look at the exponent, 7. That tells me that I need to move the decimal 7 places, and I move it to the right because it's positive 7. Then I fill in the gaps with zeros and rewrite my final number without all the chicken scratch, 93,745,000 miles. It's pretty far. What about for small numbers? Here is the mass of an oxygen molecule. I'm not even going to say that number. Again, we want to move the decimal to just after the first meaningful digit, in this case, just after the 5. and then we count how many places it has to move to get there. I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So we write 5.31 times 10 to the negative 23 grams. Here, the exponent is negative because we moved the decimal to the right. And finally, let's convert a small number from scientific notation to standard notation. Human hair comes in lots of widths, but a typical width is 7.2 times 10 to the negative 5 meters. Just as before, I'm going to write down the magnitude, 7.2. Then I move the decimal point 5 places, because the exponent is 5. This time, we move it to the left because the exponent is negative 5. Fill in the missing zeros, don't forget to put a 0 before the decimal point, and we can rewrite our final number, 0.000072 meters. Okay, so far we have shortened numbers a lot and saved space on our paper and made numbers easier to discuss by using scientific notation. But people are lazy, I mean, people are efficient, and I want to save even more space and even more time, right? And so let's take a look. I'm going to write out a really long number here. Lots and lots of zeros. Okay? Now, you're probably familiar already with writing commas every third digit. And those groupings correspond to things like thousand, million, billion, so on and so forth. But there isn't actually a whole lot of consensus on that naming. For instance, what we in the US call trillion, the French call billion. So it can get confusing. Confusing communication is bad for everyone, but it's especially bad for scientists. So we standardized. The numbers that correspond to thousand, million, billion, and so on are 10 to the third, 10 to the sixth, 10 to the ninth. Notice that the exponent goes up by 3 each time. We call these kilo, mega, giga, and tera. And there are names for bigger numbers too, but they don't get used all that much. On the small end, 10 to the negative 3, 10 to the negative 6, 10 to the negative 9, the exponent goes down by 3 each time. We call these milli, micro, nano, and pico. And there are smaller ones, but those are also pretty uncommon. Now, almost all of the SI prefixes are linked to those groupings of 3. But there's one really common one that we will use a lot that's equivalent to dividing by 100, or multiplying by 10 to the negative 2. That's called centi, as in centimeter. So, how do we use these SI prefixes, these gigas and kilos? Let's take a look at an iPhone. Many iPhones come with 128 gigabytes of storage. You've probably heard the term gigabyte, but what does that mean? Well, a byte is a small chunk of useful computer data. As we can see above, giga is an SI prefix that corresponds to 10 times 10 to the ninth. Now you can also see this on your cheat sheet. Keep your cheat sheet accessible at all times. This table shows all of the SI prefixes, their names, their symbols, the number they represent, and the scientific notation version of that number. Here we see capital G, giga, means times 10 to the ninth. So we can simply replace the G in gigabyte with times 10 to the ninth, and we get 128 times 10 to the ninth bytes, or 128 billion bytes if we count out 9 zeros. But wait, you say, 128 times 10 to the ninth isn't scientific notation. There isn't a decimal place after the 1. It should be written as 1.28 times 10 to the 11th bytes. And you're right. It isn't strict scientific notation. But then again, rules are made to be broken. Sometimes strict scientific notation isn't the most useful. Let's look back at the human hair example, and we'll see why. Remember, a human hair is 7.2 times 10 to the negative 5th meters across. Now, if we look at the long number above, or if you guys look on the table on your cheat sheet, you'll notice we don't have a name for times 10 to the negative fifth. What gives? Well, we do have a name for times 10 to the negative sixth, and that's pretty close. So let's use it. Times 10 to the negative fifth means we've divided by 10 5 times. So if we divide by 10 one more time, we'll get times 10 to the negative sixth. But we can't just divide our number by 10, because then it won't be the same number anymore. We have to multiply by 10 as well, because that reverses dividing by 10. So we multiply the magnitude by 10 to compensate. 7.2 times 10 is 72. Times 10 to the negative fifth divided by 10 is times 10 to the negative sixth. And voila! Now we have 72 times 10 to the negative sixth meters, or 72 micrometers. So sometimes we can use a loose interpretation of scientific notation, and that's more helpful and lets us write numbers more efficiently and use those SI prefixes. Now, the last thing we need to discuss in this lesson is that base units are your friends. But what does that mean? Well, there are a few things that are pretty obvious for us to measure as people. They are length, or the distance between objects, mass, or how much stuff something has, and time, or the duration between events. Now, with these three measurements, we can actually measure everything in the universe. Okay. Almost everything in the universe. But essentially, everything else that we discuss in this class, force, momentum, torque, energy, heat, power, it can all be described by measuring length, mass, and time. And when we measure force, momentum, torque, energy, when we measure these things in newtons or joules or watts, all of those measurements, all of those units, they're based on measuring length, mass, and time in a specific way. For our system of units to work, we have to be consistent. And that means that almost all of the time, when you're working with numbers, you need your lengths to be in meters, your masses to be in kilograms, and your times to be in seconds. Now notice that the base mass is the kilogram, not the gram, which is totally annoying, but it is what it is. I guess the kilogram is just more useful for daily life than the gram is. Anyway, there you go. That is scientific notation and SI prefixes. Let me know if you have any questions, need any help, if you're super confused. Tip us out.